Welcome you all to the course on process instrumentation, dynamics and control. In today's lecture, we are going to discuss on the mathematical model of the liquid level system. So let's get started. So here we have a liquid level system. We have a tank or of uniform cross-sectional area being A, and we have a resistance to the outlet flow which is R, and then we have an inlet flow which is a volumetric flow rate entering into the tank, let it be Q, which is again a function of time T, and we have an outlet flow rate which is Q of T, it is also a function of time, and we have a time varying flow of liquid of constant density Q, and let the height of the tank be H. H is also a function of time. So we have a resistance R which is connected to the outlet flow rate. The resistance can be a valve or a wire. So here we have the relationship between the height of the tank and the volumetric flow rate, outlet volumetric flow rate, which is given by the relation Q naught is equal to H by R, where Q naught, I said earlier, Q naught is the outlet flow rate, and H being the height of the liquid level inside the tank, and R is the resistance. From this relation, you can see that this height of the liquid is directly proportional to the volumetric flow rate Q naught, and it is inversely proportional to the resistance R. So which means that if there is a less resistance, then the volumetric flow rate will be high, and if the height of the liquid level is more, and then obviously we have a high volumetric flow rate. So with this assumptions, we will start with the first principles to find out the mathematical model. So coming to the next slide, we are going to write the mass balance around the tank. What is mass balance? That is rate of mass in minus rate of mass out is equal to rate of accumulation of mass inside the tank. So here you can see that the volume of liquid that is entering into the tank is given as Q of T, and the volume of liquid that is going out of the tank being Q naught of T, and we have a constant density, and the constant cross-sectional area of the tank being given as A, and the height of the liquid is given as H. So with this we can use the variables to represent the equation, and we are going to write the equation in two different states. One is in unsteady state mode and another one is in steady state mode. So let us check how they have written the unsteady state mass balance equation. So the mass flow in minus mass flow out is equal to rate of accumulation of mass in the tank. So let us see first term, the mass flow in. Here we have the volumetric flow rate and density. So when you multiply the density with the volumetric flow rate, which gives you the mass flow rate. So the mass can be written as density into volume. So with that we are going to make use of this variables. So density is given as rho, and the volumetric flow rate is given as Q of T. So the mass flow in will be rho into Q of T minus mass flow out. In similar fashion we can write rho into Q naught of T, since Q naught of T is the outlet volumetric flow rate. And in the right side of the equation we have the rate of accumulation of mass in the tank. So here, if it is an unsteady state balance equation, so here the height is changing with respect to time. The height of the liquid level is changing with respect to time. So d by dt, dH by dt into rho into area of that tank. So which gives you the complete equation, and in the equation you can see the density being constant and it is being eliminated in the second step, so which gives you q of t minus q naught of t is equal to d into ah by dt. So this is the equation number 2. So the first unsteady state mass balance equation let us consider as equation 1. So combining these equations 1 and 2 will eliminate q naught of t. We have a relationship that q naught is equal to h by r. So in place of q naught we are going to substitute h by r. So here you substitute in the equation number 2 and to eliminate the variable q naught of t. So q minus h by r is equal to a into dh by dt, which will be the equation number 3. So this is under unsteady state. At steady state there is no accumulation, so therefore the term dh by and dh by dt will become 0. In steady state equation the mass flow in will be equal to mass flow out. So in that condition, so we are going to write we are going to eliminate the right hand side of the terminology and it becomes 0. So we write the equation as qs minus hs by r is equal to 0. Here the subscript s refers to the equation under steady state condition. So to avoid confusion we are going to write we are going to indicate the qs and hs subscript for differentiating the equations in steady state and unsteady state mode. So we got equation in steady state and unsteady state equation. So the next step, so subtracting equation 3 and 4. So we got equation unsteady state equation and steady state equation. So we are going to subtract this equation. So if you subtract this equation you will get q minus qs in the left hand side and bring all the other terms to the right hand side is equal to 1 by r into h minus hs plus a into dh minus hs by dt. This will be your equation number 5. So if we define these deviation variables as q is equal to q minus qs, capital Q is equal to small q minus qs, and capital H is equal to h minus hs. This deviation variable is nothing but how much the variable is deviated from the steady state condition. So this will give you the deviation variable. The intent of using this deviation variable will be understood in the coming topics. So equation 5 can be written as capital Q is equal to 1 by r h plus a into dh by dt. So this will be your equation number 6. Now we are going to use the Laplace transform technique for solving this equation. Since this is a first order equation, so we are going to use the Laplace transform technique to take the transform of this equation. So transform of q will give you q of s and h will be h of s and dh by dt will be s into h of s. So equation number 7 is q of s is equal to 1 by r h of s plus a into s h of s. So this will be your equation number 7. Here equation 7 can be rearranged in the standard form. So we know the standard form of the first order equation, which will be y of s by x of s is equal to 1 by tau s plus 1. So this y of s is the output variable and x of s is the input variable and 1 by tau s plus 1 is the transfer function, which can also be represented as g of s. So 1 by tau s plus 1 will be the standard form of the first order transfer function. Here we can see h of s represents the outlet variable and q of s represents the input variable. So the equation is rearranged in the standard form of the first order equation. So h of s by q of s is equal to r by tau s plus 1. Here we are taking tau as ar. Tau is nothing but your time constant. Time constant is the time taken by for the system to adapt to any changes in its input, which is defined as time constant. So the unit of time constant will be in seconds or minutes. So if you replace tau as AR, your equation will be h of s by q of s is equal to r by tau s plus 1. In the equation number 8, you can see that there is a intermediate term that is present in the transfer function, which is nothing but r. This means that the overall equation is to the input and the output, but we have obtained the intermediate equation h of s by q of s. H of s nothing but your height of the liquid level. In order to obtain the overall transfer function, we have to eliminate this resistance R by using the following steps. So if the transfer function relating the inlet flow q of t to the outlet flow is desired, as I said, then we have to use this relation. Q of s is, as we know, Q of s is equal to hs by r. So if you subtract equation number 9 and 1 and use the deviation variable q naught is equal to q naught minus q of s, you will get capital Q naught is equal to h by r. And taking transform of this equation, we will get q naught of s is equal to hs by r. So combining this equation will eliminate h of s and we will obtain the overall transfer function q naught of s by q of s is equal to 1 by tau s plus 1, which is the standard form of the first order transfer function. Here you can see the q naught of s will be the output variable and q of s is your input variable. And this is the mathematical model of your liquid level system. And the textbook is Process Systems Analysis and Control by Kaufman. Thank you.